So from the previous video on circular motion, we kind of derived, or I introduced two equations that you can use for objects that are traveling in uniform circular motion. Okay, so uniform circular motions means they're traveling at a constant velocity on a circular path. And we talked about centripetal acceleration, which equals v squared over r, or the speed of the object squared, the magnitude of that velocity squared, divided by the radius of the circular path. And then we also talked about centripetal force, which is mv squared over r. So m is the mass, and v and r are the same thing as in the acceleration, or the centripetal acceleration equation. So both the centripetal acceleration and the centripetal force are directed at the center of the circular path, or the center of the circle around which the object is traveling. So in this video, what I wanted to do is give you a couple example problems and work through those so you have an idea of how to solve problems like this that are using these two equations. So let's scroll down here to the first example. So here in question number 1, we have a sign posted before a turn on a level road giving a maximum recommended speed of 55 kilometers per hour for the turn. Okay, the curve is a circular arc with, typo here, with a radius of 80 meters. Okay, so we have our turn in the road. So you're coming down the road, and then there's going to be a turn. You have a sign posted that says, whoa, 55, slow down. And this is kilometers per hour, right? kph stands for kilometers per hour. We are told that if this part of the turn was, if this turn was like extended into a complete circle, okay, that the radius of that circle would be 80 meters. Okay, so that's going to be our R value. And in part A, what we're asked to do is determine what the centripetal acceleration is. So we want to find AC if a car takes the curve at 55 kilometers per hour. Okay, so our V equals 55 kph. Okay, what we're probably going to want to do, we're in meters here with our radius. It's always nice to kind of go back to meters per second in problems like this usually. So let's go ahead and turn our speed here, our magnitude over velocity, 55 kilometers per hour. Okay, well, there's 1,000 meters in a kilometer. Okay, and then we need to get seconds in our denominator. So there's 3,600 seconds in 1 hour. Okay, so that will successfully cancel out our units. So our hours cancel out, our kilometers cancel out, and we are left in meters per second, which is what we were trying to get to. So awesome, we can write our equal sign, and what our V ends up equaling in meters per second is like 15.2778-ish meters per second. Okay, so we actually know this turns into a pretty simple plug and chug problem because we have our equation, our AC equals V squared over R. We know our V and we know our R, so we have 15.2778 squared divided by R. We're in meters per second squared. We are dividing, or meters per second, and we're squaring that, so meters squared over second squared will be our units in our numerator. We have meters in our denominator, so, oops, we got to plug in our R, right? Our R is 80, we know that, because we were given that in the problem. Okay, so we're left with meters per second squared, which was what we want, and we end up with 2.9 meters per second squared. Okay, so A, pretty straightforward. We're given the information in the problem, so it's a simple plug and chug. The one minor detail was we had to convert from kilometers per hour into meters per second, okay, to get an acceleration in meters per second squared. Okay, so in part B, we are told that the road is wet and the coefficient of the static friction between tires in the road is 0.550. and we're asked to determine what's the maximum speed in kilometers per hour at which your car could take this turn without sliding off the road. So in part B, we're going to want to find V. Okay, so part A, we were given V, but here we're trying to find a velocity. Hopefully this velocity that we solve for is a little bit more than what the recommended speed is, because that's, when people are designing and putting up these signs, they want to make sure that even if you have terrible tires and the road is wet, that at the recommended speed, you definitely won't slide off the road. Okay, so here we got to think about in part B. Okay, well now we have a force that's been added. So here's our car. Okay, and we think about looking at this from behind. Okay, we know that our R value is still 80 meters. We're still dealing with the same turn. Okay, but now we have a force involved. Okay, and that force in this case, the centripetal force that's going to keep this car going on the curved path, is going to be the force of friction. Okay, because the friction between the tires and the road is what turns the car and keeps it traveling on that circular path. Okay, so our friction force, if we remember from that unit, is mu times n. And in this case, we're looking at our static friction force, because we want to know what the fastest speed is. So we're going to look at our max, so Fs max, which is what our 0.55 corresponds with, is going to equal mu s. And then let's change n. This is a flat level road. Did I say that in the problem? I meant, yeah, turned on a level road. Okay. Oops, I don't know why I'm down there. So we have a level road. Okay. So our normal force is just going to be the mass of the car times g. Okay. So our centripetal force is going to be equal to mu s m g. Okay. Okay, we have our equation for centripetal force, and let's see what we can do. Well, the unfortunate thing is I have a mass value in my centripetal force equation. However, if I plug mu s mg in for centripetal force, mu s mg equals mv squared over r. You'll see I have an m on both sides, so they actually cancel out. Okay, I do know r still. I know the radius of the turn. I know mu s, I'm given that in the problem. G is just 9.8, and I'm trying to solve for velocity. So awesome, I can actually just rearrange. If I rearrange this equation, okay, so let's do some rearranging here, and we can come up with an equation that solves for v. So I'm going to multiply both sides by the radius. So we have mu s g times r equals v squared. Okay, and we'll take the square root of both sides, and we get the square root of mu s g r equals v, the velocity we're trying to find. Okay, so we're going to plug in mu s, we're going to plug in g in meters per second squared, and we're going to plug in r as meters. So the answer for v that we're going to get is going to be meters per second. So let's keep that in mind. Meters per second will be the units that we get when we plug into this equation. And we're asking the problem, I think, in kilometers per hour. So we're going to have to do a conversion at the end to get back to kilometers per hour, but that'll be fine. Okay, so we plug our numbers in. So we got square root of 0.55, that's our mu, times 9.8. Okay, times the radius is 80. Okay, and we get a value of v that is 20.7765-ish meters per second, and I will round at the end after we convert to kilometers per hour. Okay, so the last thing we need to do is convert to kilometers per hour. So write down what we're given, or what we've figured out, 20.765 meters, it's about 20 meters per second Okay, so we have 3,600 seconds in 1 hour. That, oops, I don't know why I crossed that out. Don't want to cross that out. I want to cross the seconds out. That's what canceled. And to get meters to kilometers, we know there's 1,000 meters in 1 kilometer. Okay, and then we do our multiply across and divide by 1,000, and we get 75 kilometers per hour about. Okay, so that checks out. That seems reasonable. The recommended speed around the turn was 55 kilometers per hour, which definitely should be safe even in rainy conditions, with a coefficient of friction of 0.55 between the tires and the road. Okay, so that's the first example problem, and that problem included a part where we used, so part A used our centripetal acceleration equation, and part B used our centripetal force equation, which they do look very similar. Okay, so moving on, I have a second example here. So in our second example, we have the International Space Station, which orbits the Earth approximately 400 kilometers above Earth's surface. Just a nice picture. And what keeps the ISS in orbit, okay, so this is not going to be to scale. So here's Earth, okay, those are some oceans on Earth. And here is the ISS in its orbit around Earth. Not to scale again, the ISS would be the orbit would look a lot closer to Earth. It'd be, because the scale is wrong here, but let's just go with it, okay? So the ISS is traveling at a constant speed, okay? And we don't know what that is. We're not given that, but it does say that it's a constant speed. So in this orbit, it's traveling at a constant speed. So if we drew those velocity vectors, they would be the same length. And we're told that Earth's gravity is, and obviously Earth's gravity is what's keeping the space station in orbit. So our centripetal acceleration in this case, all these ACs are going to equal the gravity, the acceleration of gravity. Okay, and I'm going to put A sub G here because it's not our 9.8 number because we're up at such a high altitude. So our A centripetal acceleration is going to equal gravity, the acceleration due to gravity up at 400 kilometers of altitude. Okay, that means the 400 kilometers is just how far above Earth's surface the space station is. Okay, so that's 400 kilometers. At that altitude, the acceleration of gravity has decreased down to 8.67 meters per second squared. And we're going to look at this later, kind of in the unit, at actually calculating what the acceleration due to gravity would be at a certain altitude above Earth. Because 9.8, we talked about, we've been using 9.80 meters per second squared. But when I first introduced that, we said, hey, this is a good approximation for on Earth's surface at around sea level. But here we see at 400 kilometers up, it's quite a bit, it's significantly less. Okay, so our centripetal acceleration we know, okay. That's awesome. So by reading the problem, that's kind of the information I'm given. What I'm trying to find is how many minutes it takes for the ISS to complete one trip around the Earth. I'm given, oops, I did miss one little piece of information I'm also given that the radius of Earth, and here you can see this is really not to scale, this radius is equal to 6,378 kilometers. Okay, so let's think through how we can solve this problem. I know the centripetal acceleration, okay? I know the radius of Earth, and I know that it's 400 kilometers above the Earth's surface. So I know my radius of the path, okay, of the orbit is going to equal 6,778 kilometers. Okay. But I want to find the time. Okay, so how can I do this? Well, I can use I can use the fact that I know centripetal acceleration equals v squared over r. I can use that to find the velocity or the speed. So I can find the speed. Okay, if I can find the speed, okay, I actually can find the time because I know the radius of this circle, of the circular path of the satellite around the Earth, and I can use the fact that the distance around, okay, so so the distance around this path, that's just the circumference of a circle, right? So let's call this S equals path length for one orbit, just equals the circumference. Okay, so S is going to equal 2 pi times the radius of the path. Okay, so if I know the distance and I know the speed, well, I know that that basically distance equals rate times time, that S is going to equal v times t. Okay, and if I rearrange that, I can solve for time. So that is my plan here, folks. I'm going to first solve for v, okay, and then use, oops, what am I doing here? Time equals S divided by v. Okay, so I can use my centripetal acceleration to find v, and then I use my knowledge of the radius of the path to find the circumference or the length, the path length of that orbit. Okay, and I can use my knowledge of distance equaling the rate times time, or in my variables it's S equals v times t. So I can rearrange to solve for time. So that's the plan. Now let's carry out that plan. So we have, first we want to use v squared over r. We want to rearrange this for solving for v. Okay, so if I take my centripetal acceleration and multiply it by the radius and take the square root, that will give me the speed, or the magnitude of the velocity, and those numbers I know are 8.67 meters per second squared, and I'm gonna have to make this longer. Okay, and I know my oops, I need to be consistent here. I've called this RP, so let's add a little p. The radius of this path that the ISS is taking is given in kilometers, but since I'm in meters per second squared, I need to add 3 zeros to turn this into meters. 7, 8, 1, 2, 3. Okay, and when I do that on my calculator, I end up with 7665.85-ish meters per second. Okay, so that's cruising. That's 7.5, a little over 7.5 kilometers a second. It's pretty fast, guys. Okay, now that I have solved for v, so this is v. Okay, now I need to know how far it is for the ISS. Here's my ISS. For the ISS to go around the Earth one time. Okay, so we know RP, and we said that is as simple as just finding the circumference. So 2 pi times RP equals 2 pi times, again, we want this in meters to be consistent. Okay, so the final step was, we know that velocity times time will give us the distance. So we know our distance. If we divide that by the velocity, so 2 pi too lazy to do this intermediate step on my calculator. Okay, so 2 pi, that's our 2 pi times 6778000. That is our distance traveled in meters. Okay, and we know our velocity was 7665.85 meters per second. Okay, so my meters are going to cancel, and 1 over seconds is, if we're dividing by 1 over seconds, we end up with seconds. So this is going to be equal to the time in seconds. Okay, and what we end up getting is 5555.47 seconds. But we are asking the problem to give our answer in minutes. Okay, and minutes will make more sense because we don't really have a good, at least I don't have a good idea of what 5,555 seconds is off the top of my head. I need to do some quick math. Okay, so we have 60 seconds in 1 minute. And seconds cancel. We're ending in minutes, and we end up with about 93 minutes. Okay, and so if you Google this, is actually what you would also find. You could Google this answer as well. But the fun thing is, you can knowing the altitude, and knowing the gravitational acceleration at that altitude, you can actually figure out and mathematically determine the amount of time it takes the ISS to complete one trip around the Earth. Okay, so those are 2 examples with using our equations for uniform circular motion. Hopefully this was helpful.